hands down, my favorite part of teaching physics to life science students is learning the cool stuff that the body has evolved and is capable of. It never ceases to amaze me. We have this absolutely amazing machine that we're all born into. And if there's any good reason to take care of it, it's because it finds so many great ways to take care of us. Okay? So one of those ways is that our bones are able to be so sturdy and so powerful that we can do all these things and like lift things and play sports, right? But they're also just bendy enough. They're just compressible enough so that they don't break easily and they absorb some of our shock, right? So in this problem, we said that there's a young child who weighs about 35 kilograms, right? Falls from a tree that he's climbing that's 4.7 meters high. So here's our tree. We have a tree right here, right? And there's a branch on it, right? Okay, and it's 4.7 meters high, right? And when he lands, right, his bones compress a little bit. So he starts out here, that's R1, right, with that potential energy. And after he falls and he lands on the ground, right, that potential energy has to be absorbed by the bone, right? It has to go somewhere, right, because he comes to a rest. So that energy is absorbed by the bone, right, in the same way that a spring would, all right? So the question is, by how much would you expect his femur and tibia to compress when he hits the ground standing, okay? So we're going to approach this like we would all the other conservation of energy problems. He has a certain energy that he starts with, and conservation of energy says that there's a certain energy that he ends up with. Okay? So the boy on the tree branch starts out with what kind of energy? By this time, gravitational potential energy, right? He's 4.7 meters up off the ground. Okay? And at the end, the energy that he ends up with is this stored potential energy, this elastic potential energy stored in his bones, right, that they absorb. So that's going to be, this is gravitational potential energy, and this is going to be elastic potential energy. Okay? Step 2 of these problems is always to substitute your equation. Well, we know gravitational potential energy is mass times gravity times height, right? And we know that elastic potential energy is 1/2 spring constant times x squared. Okay? Where x is the actual compression of the femur and tibia. This is what we're looking for. Okay? Well, do we know the boy's mass? Sure do. It's 35. Do we know gravity? Sure do. It's 9.8. Do we know the height of the branch? Absolutely. It's 4.7. And do we know the spring constant inside a femur? Well, a typical bone, and they vary, but a typical bone is about 1.7 times 10 to the 7. And that's specifically for a femur, okay? Because different bones have different thicknesses and they're formed slightly differently. But for a femur, we're looking at 1.7 times 10 to the 7 times x squared. And so we're just solving for x here. So do our algebra, multiply by 2, divide by 1.7 times 10 to the 7, take a square root, and I get about 1.4 centimeters. Okay? That's 0.0014 meters, but 1.4 centimeters. So it's conceivable that when you fall from it's a pretty good distance, right? That's a little over 20 feet. And if someone were to land on their feet that way, you're actually compressing about 1.4 centimeters. That's like that much, right? That is one of the amazing things about the human body, that it's capable of protecting us in so many ways. For those of you who have studied biochemistry, you probably know just the sheer number of ways, just chemically, that the body is constantly protecting us. And anyone who studied microbiology knows how many ways that our gut biome is contributing to our immune system and protecting us with little bacteria and microbes. So yeah, let's end on that positive note that our bodies are amazing. And I will see you next week for Momentum in Center of Mass.